So we're going to be talking about unit availability and mitigating the costs of failures, because failures do occur and will occur. So unit availability is paramount for multiple reasons. Many of you guys are coming from utilities, and you're there to make power for a purpose of grid reliability, generation revenues. If your unit's not online, you're not making money. Also, on the other side, not just revenues, but on fines. With strict and frequent planning of generation, an unplanned outage can result in hefty fines. And also for water conveyance purposes, downstream users, irrigation canals, rafters. We've seen plants with multiple levels of redundancy just to make sure that you're not leaving kayakers on rocks. So all of these lead to fines, lead to unit availability concerns. Now, why is this relevant now? There is a trend, as most of you know, towards modernizing controllers. And this can be SCADA systems, unit controllers, excitation systems, governors. I'll probably reference governors a little more because that's what I'm familiar with, but these principles will apply to all types of modernized control. So if you have a relay board and a pilot exciter and a mechanical governor and you're replacing it, there is no equivalent replacement to what you have right now. So engineering decisions are going to have to be made about what you're putting into place. This opens the door to not just moving from something that you know and are comfortable with, but to something that you're maybe not as familiar with, and you're not sure how reliable it's going to be. Also, if you are familiar with modern digital controls, you know that this opens the door for the opportunity to make improvements in your reliability. I'm going to talk about a few definitions that we're going to talk about through our presentation. Some of you guys may have seen before, some of you may not. First one, mean time between failures. This is the average time between component failures. Anytime any component in your system fails, that's considered a failure. It may not mean that the entire system fails, so it's a measure of the reliability of your system. How often do you have to work on it? How often are you seeing problems? Mean time to repair. This is the average time required to repair a failed component. How maintainable is your system? Is it easy to fix? Do you have to call in the experts from the regional engineering offices just to get it back online, or can your local technicians take care of the problem? Mean time between forced outage. This is the most important one. This is the average time between a total system failure. This is the average time between a unit coming offline and not being able to generate for you, causing those fines. And this is a measure of availability of the system. This is what we're mostly going to be concerned with. The final one, barely doesn't really need to be on here, but cost. The total cost to design, procure, install, operate, and maintain the system throughout its life, not just the upfront cost of the materials. And we're going to look at several different options for installing control systems, ranging from a fully simplex system where you have single inputs, single power sources, going into a single controller, driving a single set of outputs. A little more complex, maybe you have redundant sensors, redundant power supplies, redundant power sources, all still going into a single controller which has a single set of outputs. And then finally, fully redundant control systems where you may have multiple sensors going into multiple controllers which are comparing data or voting and then sending control signals to maybe multiple outputs which are in a passive configuration where you have a primary and a backup control system. And we'll talk about each of these, and then we'll talk a little bit about where they may be applicable. So, fully simplex equipment. This is as simple as it gets. 10 simplex. You have the minimum number of components required to make up a system. If you have a power supply, you only have one power supply. If you have a pressure transducer, you only have one. These are the simplest and the cheapest to design, the cheapest to implement and maintain. So therefore, you'll see that with the minimum number of components required, you'll have the highest mean time between failures. That's good. You'll run the longest before you have a component failure. Because they're simple, you'll have the lowest mean time to repair. They're easy to work on, they're easy to understand. Your normal plant technicians can replace equipment. But they are the riskiest to operate because any single component failure can cause your entire system to come down. So they do have the lowest mean time between forced outages of the three we're going to look at. But they have the lowest cost. They're simple. So, if you want to increase your availability more than a simplex system, it's the next logical step. You want to duplicate the components that are most likely to fail and the components that are easiest to duplicate. And that's typically your input signals and your power sources. Your power sources, because as most of you know, power sources are the most likely to fail. Power supplies, fuses, breakers. And they are easiest to implement because with most redundant configurations, there's no logic involved at all, just monitoring. Inputs are a little more complicated, but not much. You can bring 2, 3, however many pressure transducer speed signals into your controller, have a high signal select or voting algorithm, choose a single best signal, and then the rest of your system remains unchanged. So your mean time between failure does rise because you have more components. So you will have more. If you have more components will fail more often. You'll have more failures just by probability. Your mean time to repair will go up a little bit. Not much because it's a simple integration. It's not that much harder to replace a power supply when you have one power supply as when you have two, though it may get a little more complicated. But your mean time between forced outages will definitely go up. And this is because you have increased availability from two sources. Obviously, your redundancy. If one power supply fails, swap over to the other one. You keep running. But also increased availability from additional diagnostics. If you have two pressure transducers and they disagree, you know you have a problem. If you only had one and it was off or was miscalibrated, you might not know you have a problem. So there's a whole another level of diagnostics and information that you gain just from simple redundancy. Now, step past this is full-blown redundant control. And there's actually several layers here we're going to talk about. The simplest is redundancy of your controller's CPU only. Next level would be a full redundant controller, including CPU and I/O. And then finally, looking at your output device. These controllers, through the spectrum from the simplest to most advanced, will lower your mean time between failures. Again, same trend. More equipment, the higher probability that you're going to have a failure. It will raise your mean time to repair because your system's getting more complex. But it will also significantly raise your mean time between forced outages because you're striving towards that kind of ambiguous goal of no single point of failure. And your cost will be the highest, not just in equipment cost, but design cost, implementation cost, and maintain cost. So these three options. If anyone who's implemented a new control system, say you're going with an Allen Bradley controller and you want redundancy, the first thing you're going to look at is, well, what's their solution for redundancy? And most PLC manufacturer solution for redundancy is CPU only, which is one of the things that's attractive about it. It's a CAN solution. It's easy to implement. You pretty much plug and play the components, select the box and the software that you want redundancy, and there you have it. There are some downsides that need to be considered, though. These systems are not really designed for single system controllers. They're more designed for a master control unit running, say, 5 bottling lines in a bottling plant. So they're not designed for a single system, a single exciter, a single governor, a single unit controller. There is some decreased PLC performance in the overhead. They're not designed for speed optimization. And you still have many single points of failure. One I/O module is still going to take your unit out. So while you're replacing your CPU, it's just one component. So the next step will be, let's have redundant I/O across the board. And usually you'll see this in 2 fully redundant controllers running the exact same set of hardware, running parallel programs that are operating in sync. Now these often do require custom engineering, but because of that, they can be optimized and configured for your arrangement. So your performance impact is minimal. It's going to be seamless to your normal operation. And in your controller, you'll now have no single point of failure. Any controller component can fail and the unit will keep running. You'll lose some robustness because you've gone to your backup, but you can now take an outage at your convenience. This still leaves single points of failure. These 2 controllers come to consensus and say, okay, we're going to open this actuator. Well, what happens if the relay that opens the actuator fails? Or what happens if the valve that opens the actuator fails? And this is where things really start getting into a gray area, kind of going down the rabbit hole of where do we stop? And you need to look at the device, look at the likelihood of it failing, look at the cost of it failing. You'll often see redundant hydraulic controls. You less often will see redundant relays because of fail-safe logic and how they operate. It can get really complicated and give intermediate states of failure. So this is where, I'm not going to go into much more detail, but can you really eliminate every single point of failure? What are you trying to solve just a mantra of no single point of failure? Are you actually making serious improvements? And then also, what are your common modes of failure where if you're talking about field devices, you're talking about devices that, say, dirty oil going to 2 valves, maybe having 2 valves isn't giving you that much bang for your buck anymore. Okay, so when would you want to use these types of systems? They're all valid configurations. So I'm going to choose a few utilities we've worked with and show you their situations that drove the decisions they made. Brookfield Renewable Power has many hydro installations in New York and Maine. Many of them are under 10 megawatts, small units. So they chose fully simplex equipment. One power supply, one controller, one output. They have, at under 10 megawatts, their lost generation costs are less. If their unit goes down, they're relying on that energy, but they have 40 other units in a 20-mile radius that are also generating. So your cost for a single loss is less. And there's less impact of that loss. These units are regulated less, so there's lower fines. They're not required to pass the same quantities of water. So failure is tolerable. The next level, we're doing a project with the Army Corps of Engineers and in the Pacific Northwest. Most of their units are in the 50 to 100 megawatt range. The lost generation costs are starting to go up at this point, where a unit going down at 100 megawatts in the peak of summer is a significant impact. But in their favor, these plants have redundant units. So maybe unit 7 goes down, unit 8 wasn't running at the time, they can bring that up. So there's a level of backup there. So these aren't critical failures, they're costly failures, but they will not result in any significant fines, and there are backup options. That's why they choose redundant sensors and power supplies. And it's also the best bang for your buck. It's the easiest to implement, and it gives you the biggest boost in availability for the least cost. Now the final situation, Pacific Gas and Electric in California, has a lot of large units, a few large units, over 400 megawatts. They also have a lot of water conveyance responsibilities. These are the guys who are California, the valley, irrigation, recreation. If they can prevent a single forced outage that results in a loss of flow, that might cost them $100,000, $200,000. If they can prevent a single event by going with a redundant system, it pays for itself. These are the situations where redundancy really comes into play. You'll hear it, I mean, you wouldn't think twice about redundancy on the plane you flew in on because it's a loss of life situation. Anywhere where a failure is not acceptable, that's where you're going to see redundancy. Now, on top of the decision making of what level of redundancy, there are other steps you can take to minimize your mean time between failures. One thing you saw as a trend is as we increase equipment, you'll have more equipment failing. So minimize the number of components across the board during your design. Use high quality industrial grade equipment. Use protection, clean oil, clean power, filter your oil. And then a well-maintained, well-executed preventative maintenance plan will minimize the failures that can take your system out. So when equipment does fail, how can you minimize the amount of time it takes to repair it? One of the biggest advantages of modern control equipment is its enunciation power, where if you had a mechanical governor and you had a cable stretch and now it's out of calibration, you're not going to know about it. A modern governor will enunciate on that immediately, send an alarm not only to the local operator, but into your SCR and into your asset management system, whatever you're running. So with clear enunciation, you can identify where the exact cause of the problem is quickly, if that's set up properly. And then obviously training of the staff, the troubleshooting and replacing components practices. A lot of new equipment is being placed that the existing staff is not very familiar with. And thank you. And getting them trained. Available spare parts, not just stocked, but functional. How many of you guys have a spare parts shelf that's full of dust and the equipment was sent 20 years ago, and who knows if it works when you're going to need it? And then the components that are easy to replace. Finally, the steps to minimize mean time between forced outages, and this is really coming from your redundancy. You have various levels of redundancy that you may not even know about with redundant units, where if unit 1 goes down, you can put unit 2 online if your generation planning allows for it, all the way through control algorithms, where maybe you can swap from an automatic control manually into a manual control and keep that unit online without replacing any additional. So between the various levels of configuration and some of these steps, modern controls can greatly enhance unit availability if that's the design point in the beginning and it's a logical design point, not just with a we want this unit available 100% of the time. Thank you.